This Chapter 4 reviews a standard pricing model for callable bonds, focusing on both European and Bermudan alternatives by means of binomial trees. Worksheet Callable Bond Low Vol requires a little background explanation before we dive into its details. The binomial process described in this worksheet centers around the idea that future scenarios for the path of interest rates, in this case very specifically the 1-year zero coupon rate, can be modeled if we have already first the current 1-year rate, two, a credible input for the expected future volatility of this 1-year rate, and very importantly, three, observable market prices for bonds spanning a reasonable range of maturities into the future, enabling us to calibrate the model, essentially meaning to ensure that its predictions in the tree at the top for the 1-year zero rate are consistent with the observable market prices for these outstanding bonds. So we begin by assuming prices exist for, in this case, 1, 2, 3, and 4-year bonds, the last three of which we just showed as we gradually crawled down the worksheet, along with their annual coupons listed next to them. And of course, the 1-year bond itself, being a discount security, therefore pays no coupon and yields its 3.5% return, visible in this cell C6, entirely via accretion from its discounted price to par. As you can see, therefore, the pattern appearing here indicates a normal, i.e. upward sloping, par curve. Our last assumption appearing in cell I4 is that the future volatility of the 1-year zero coupon rate will be 10% annualized. Finally, we point out that in practice, a tree like the one here would have many more time steps than we have shown, of substantially shorter duration, with the precision of the model increasing as we increase the number of time steps. Our next task is to model the future possible paths of this 1-year rate over the next 3 years, focusing on its possible values on each anniversary date during those 3 years. Starting on this row 4, you see a tree which displays a binomial process for this 1-year rate, shown to be 3.5% initially in cell C6, and then migrating, as it were, towards one of two values a year later, appearing in cells D6 and D7, respectively, which we can think of in a general sense as the high and low values to which the 1-year zero rate might migrate over the next year. This being a binomial tree, only two values are allowed as successors to the single previous value a year earlier. but more sophisticated models involving trinomials are sometimes used. For now, what we have done is simply guessed that the value in cell D7, i.e. the low value, is 5%, and then tied the value under the high scenario in cell D6 to this lower chosen value of 5% by multiplying, as you can see in the formula, this low value by e to the power 2 sigma to derive the high value, sigma being, of course, the 10% volatility assumption we began with, appearing in cell I4. Note that the greater the assumed volatility, the further apart the two alternative values would be, the high and the low, consistent with how all binomial models work for the pricing of any kind of option. Note also that even the lower number in year 2, i.e. the guess, need not be assumed to be smaller than the spot rate in the previous year of 3.5%. All that the model requires is that it be smaller than the high alternative appearing right above it, and so on the further up we go in any column. And the e to the power 2 sigma operator makes sure mathematically of delivering this result. Moving one more year into the future brings us to the three cells E6 to E8, which again are linked to one another, with the bottom cell containing our guess, set this time at 6%, above which lies a number derived from it via the e to the power 2 sigma multiplier, and above which lies another number also derived from the previous one via the same multiplier. You can, if you wish, think of these as the low, medium, and high alternatives for that point in time, or node as we call it. The process continues each time you move one node further towards the right, but with this particular tree, of course, we only have one remaining node in which we have inserted a guess of 7% in cell F9. Then in each cell above that, the usual formula linking that cell to the one immediately underneath it via the 2 sigma multiplier. At this point, we have a tree that spans the entire 3-year period under consideration, and in principle we could continue into longer and longer maturities for as long as bonds having those maturities trade in the market at prices we can confidently observe and use. In addition to being linked vertically, the cells in the tree are also linked horizontally, with the number in one cell having a 50-50 probability of migrating a year later to either the cell immediately to its right or to the one immediately underneath that. So to illustrate, it is deemed 50-50 probable that the 7.3284% in cell E7 will migrate a year later to either 10.5 44.28%, or to 8.54 98%. The 1-year chosen interval here is responsible for the wild movements in rates deemed possible by the model, and greater precision in its workings, such as by insisting on shorter intervals between nodes and possibly a third option at each juncture for what happens next, hence trinomial, but requiring greater computational efforts, would achieve more accurate outcomes with greater credibility. We now turn to the calibration of our tree, which means in essence that we use the data available in the bond prices and coupons to confirm that the guesses we have made in the bottom cell of each column are consistent with these bond prices, and if not, then to change the guesses so that any inconsistency is eliminated. This will involve a so-called inductive process, which will use the outstanding 2-year bond to calibrate the rates in column D, then the 3-year bond to calibrate the rates in column E, and finally the 4-year bond to calibrate the rates in column F. We will then have a fully calibrated tree, i.e. one suffering from no inconsistency, which we can use to price straight, callable, and puttable bonds with reasonable ease. The tree you see starting on this row 13 attempts to model the price behavior of the 2-year bond with a 4.2% coupon. As with the binomial trees we used to price FX options in the module bearing the same name, we begin with the last column on the right, i.e. column E, which simply states that the value of this bond at maturity, or 1 second before maturity to be more precise, can only be the sum of its face value plus 1 year of accrued interest, therefore 104.2, irrespective of which scenario has been reached for the 1-year rate on that date. Note that the model ignores default risk altogether. Taking another page out of the binomial tree approach from FX options, we now focus our eyes on cells E17 and E18, and then on cell D17, their predecessor in time, so to speak, and we model the clean price of this bond 1 year ago as simply the discounted PV of the arithmetical average of the values in cells E17 and E18, as you can see if we open the formula. Note that use of the arithmetical average is consistent with the 50-50 probability assumption we mentioned earlier, and would need amendment in a model that incorporated different probabilities or trinomial outcomes. The other key point here is that the appropriate discount rate to use to calculate the PV of this average is not the spot 1-year rate of 3.5%, but rather the projected or forward 1-year rate appearing in the appropriate cell of our original tree, which in the present case is the 6.1070% in cell D6. Finally, the formula recognizes that on that date, an entire year's coupon would also be payable to the holder, so adds that amount to the total value via the reference to C15 that you see here in the formula. Backward induction, as it is called, now takes over, which means the process is repeated one column at a time as we gradually move further and further towards the left, in each case making sure to add the coupon that has accrued to the discounted average calculation and to use the correct discount rate from the original tree that matches our position in the present tree and the correct point in time at which we stand. You can see in cell C17 that this leads us to an initial price for this bond of 99.44, which is inconsistent with the observed price of 100 we mentioned at the beginning. Note importantly that in the formula for this one cell, we do not add accrued coupon, since we assume that this has just been paid and so is no longer part of the price. Since every step of our process is actually pretty correct, the only explanation for the inconsistency between the theoretical and the observed prices for the 2-year note is that the guess of 5% appearing in cell D7 was inaccurate, and that it needs to be adjusted to that level, presumably slightly lower, that would increase the various calculations of PV throughout the bond's binomial tree and pull the price up in cell C17 to 100 exactly. Observe importantly that in this example, 100 just happens to be the price observed in the market for the 2-year bond. But if the bond were trading at a premium or discount, we would use that premium or discount instead of par. We now resort to our old Excel friend goal seek, setting cell C17 via goal seek to value 100 by changing cell D7, and now hit OK, revealing a rate of 4.4448% in lieu of our previous 5%. The other value in column D, lying right above the first one, and specifically in cell D6, of course adjusts automatically to this first change, since it is linked to it by means of the EXP 2 sigma multiplier, which is constant. We consider this column now fully calibrated to market prices and move on to the one immediately to its right, containing this time 3 values for the 1-year rate in 2 years' time instead of just 2 values. To calibrate this column E, which lies 1 year later in time than the previous one, requires us presumably to resort to the 3-year bond, which again we assume is trading at par, but this time has a coupon of 4.7% annually. beginning with the rightmost column, which shows this bond's redemption value including final coupon, and working our way towards the left one step at a time, remembering always to use the discount rate from our original tree matching the node at which we stand, and also to add in each cell's formula the accrued coupon for 1 year, leads us once again to a single spot price for this bond, appearing this time in cell C26 as 98.638. Again, since the observed price in the market is 100 exactly, we goal seek to this value. Thus, tools goal seek to value 100 by allowing the entry in cell E8, previously another guess that we had to make, to change, and then we hit OK to discover the solution 4.6958%. Incidentally, if you try this, you may get a very, very small difference due to the number of decimals of accuracy in which you have programmed Excel. Note that cell E8 was the only one really that we could permit to change. The ones directly above it are derived from it, while the ones in the column to its left have already been fully calibrated, so are no longer eligible for change, and the ones to its right are too far into the future. By now you should permit us to move faster as we use our final bond, the 4-year bond described starting on row 32 and with the 5.2% coupon, to calibrate the last column of our tree, we note in the table for the 4-year bond that the spot price currently appearing in cell C36 is 97.921, substantially below the observed par price. Goal seek to 100 by changing cell F9 once again leads us to a solution, this time of 5.0483%, as you see here. We have completed the calibration of our 3-year tree at the top for the 1-year interest rate, and can now use this to price a variety of bonds with embedded call and put options, European or Bermudan style, coupon step-ups, and other unusual features. But just before we do that, and as a reality check, we price another 4-year non-callable bond appearing in the table beginning on row 43, but one that carries a coupon of 6.5% this time, and is in all other respects identical to the one immediately above it. Knowing that the modified duration of a 4-year bond at these types of coupons and rates should be around 3.5, we estimate crudely the price premium at which this bond trades relative to the preceding one with the 5.2% coupon and trading at par to be around 4.5 points given the 130 basis point coupon advantage of the second bond, and presumably a little higher once convexity is remembered. We now turn to the tree beginning on row 47 and work our way through the formulas in each cell until we reach a spot price of 104.643, i.e. a premium over par of 4.64%, very much in accordance with our armchair estimate that used modified duration. Our tree appears well calibrated and ready to assist us with more complex bonds. The tree beginning on row 54 models a 4-year bond with a 6.5% coupon once again, but this time the bond is callable on any anniversary at par plus accrued interest, of course. Intuitively, we know that since the investor has granted the issuer an option to prepay the bond on any anniversary, but the coupon has not risen to compensate for this prepayment privilege, the value of this callable instrument will be less than the 104.643 we calculated for the non-callable alternative. Indeed, we can generally depict a callable bond as the combination of its non-callable version minus the call option, whether European, Bermudan, or American, that the investor has granted to the issuer. And we can write generally callable bond equals non-callable bond minus call option. The art, of course, is to value the call option, but the algebra is impeccable and guarantees that the callable instrument will be worth less than its non-callable version in 100% of cases, all other features being the same. Puttable bonds, incidentally, which the holder can sell back on specified dates at par or some other price to the issuer, can also be deconstructed algebraically into a straight bond and the put option. But since this time it is the holder that owns the put option, we would write, in contrast to the callable version, puttable bond equals non-puttable bond plus put option. The principal feature we introduce in the tree starting on row 54, which reflects the issuer's right to call the bond at par, is to stipulate that should the price in that cell obtained under the normal formula exceed the call price plus accrued interest, i.e. 106.5 in this instance, which would of course give the issuer an immediate arbitrage, since he could call the bond by paying 106.5 and then sell it for this higher price. The market, in its wonderful efficiency, would preempt this arbitrage by refusing to price this instrument above 106.5. Stated differently, no rational investor would ever agree to pay more than 106.5 for this instrument on any call date, no matter what the formula says he should be willing to pay, since that investor would face an immediate loss when this bond is called away from him at 106.5 exactly. This amendment is implemented, as you may be anticipating, via an Excel min operator appearing at the beginning of the formula, which says in effect that the price of this bond on any call date is capped at the call strike of 100 plus accrued interest to prohibit the riskless arbitrage that would otherwise become possible. The fair spot price of this bond, appearing in cell C59, is revealed to be 102.899, so some 2% below the non-callable bond, consistent with our earlier intuition described in the formula we just discussed. We pause for a second and ask you to predict what would happen to the spot price of this bond if we increase the vol input from 10% to 20% in cell I4. Click pause while you think about this, but for no more than 20 seconds, please. Since in our equation above we wrote callable bond equals non-callable bond minus call option, and we know that the value of the call option, like that of any vanilla option, increases when vol rises, it follows that the increase in vol will reduce the value of this bond even further, pulling it down closer to 100 in price. Moving over to worksheet callable bond high vol, the substitution of 20% for 10% in cell I4 is certainly the first step of our exercise, but it is not sufficient in itself. When we make this substitution, the spot prices of each bond change, in sympathy with the changes in our original tree. We need again to recalibrate all values by solving once again sequentially for the interest rate at the bottom of each column that pushes the price of each bond again to its observed value of 100 in the marketplace. We now illustrate this in quick strokes in front of you, but without much commentary. Thus, tools goal seek, set cell C17 equal to 100 by changing cell D7, hit OK, reveals a value of 3.9679% for cell D7. Goal seek again, set cell C26 equal to 100 by changing cell E8, reveals a value of 3.7492% for cell E8. And finally, tools goal seek, set cell C36 equal again to value 100 by changing cell F9, reveals a value of 3.6144% for cell F9. We are back to full calibration, and the spot price of our bond appearing down the worksheet in cell C59 is now revealed to have dropped to 102.108 from 102.899, consistent with the increase in vol. We return to worksheet callable bond low vol with the 10% vol, we remind you, and consider now the case of another 4-year callable bond identical to the previous one, except that the issuer must repay 102 plus accrued interest if he exercises the call after 1 year, 101 plus accrued interest again if after 2 years, and finally 100 plus accrued interest if after 3 years. We remind you that this feature is common to discourage early redemption, or at least compensate the investor, if it does happen, for her previous efforts by paying her this little extra amount for her troubles. Intuitively, the increase in the strike price of the call for the first 2 exercise dates diminishes the value of this call. So given our equation callable bond equals non-callable bond minus call option, we anticipate an increase in the spot price of this bond versus the previous version. The tree beginning on row 73 models this latest version of this bond. Note the separate strikes for the call option depending on the date of exercise. Otherwise, the tree works identically to the one we have seen already. As expected, the spot price of the instrument has risen to 103.942, reflecting the diminished value of the call feature. Finally, starting on row 82, we model a bond callable at par every year, but whose coupon begins at 5.5% for the first 2 years, then rises to 9.5% in years 3 and 4, assuming, of course, it is not called. The price of this instrument is revealed in cell C86 to be 102.453. If you compare this bond to the one that was callable at par every year, but carried a constant coupon of 6.5% annually, and was shown to be worth 102.899, you will readily identify the obvious trade-off. You earn 1% less under this version for the first 2 years, then potentially 3% more in years 3 and 4 if the bond survives long enough. It is, however, not enough to compare the PV of the extra 3% to the PV of the foregone 1% and deduce that this instrument under this simple PV analysis offers the greater value. The point is that the likelihood of actually receiving the high coupon in the last 2 years is diminished by the substantial probability the bond will have been called by then. What is involved is a sort of probability-weighted comparison, and our tree is set up already to enable this comparison by solving for the entire investment's fair value, revealing a spot price of 102.453, so in fact pointing to a slight decline in value from the fixed coupon alternative. We have comprehensively illustrated the use of the binomial approach to model bonds with a variety of embedded options and step-up clauses. In one of the quiz questions in Chapter 6, you will be challenged to adapt this binomial model to price a bond that may be put back to its issuer at various prices by the bondholder. But for now, we bring this Chapter 4 to an end, as well as Part 2 of this module.